Hey everyone, before we dive into the deepest mysteries of the universe, take a moment with me. As you're listening to this, comment where you're from and what time it is, and ponder how these fundamental questions about space and time resonate with your own experience. We live in a world where things exist here or there, and now feels distinctly separate from then. A world of causes and effects, where influence spreads from one point to another, but only ever at a finite speed. This is the bedrock of our everyday experience, the seemingly unshakable foundation of reality. But what if that foundation, at its deepest level, isn't quite so solid? What if the very notions of here and there, of now and then, are merely illusions? What if everything, from the smallest particles to the grandest galaxies, is secretly connected in ways that defy our wildest imagination, and even the speed of light itself? Prepare to have your perception of reality gently, but fundamentally shaken. Because in this series, we're diving into one of the most profound and mind-bending discoveries of modern science, non-locality. We'll explore the experimental proof that shows the universe is far stranger and far more interconnected than anyone, even Einstein, dared to believe. Is everything truly secretly connected? Join us and find out. Take a moment and listen. Right now, wherever you are, you're experiencing the world in a way that feels utterly natural, utterly intuitive. A world of cause and effect, of here and there. A world where things happen at a specific location and their influence spreads outwards, but only ever at a finite speed. This is the world of locality, and it's the bedrock of our everyday experience. Think about it. If you push a domino, it falls, and then it knocks over the next domino, and so on. The effect is passed along step by step, from one physical location to the next. The first domino doesn't spontaneously knock over the last one without a chain of intermediate events. If you throw a baseball, it travels through space, and its impact is felt only when it physically collides with something else. It doesn't magically appear in the catcher's mitt without crossing the distance in between. The light from your lamp illuminates your room, but it doesn't instantly brighten a room on the other side of the planet. It travels at a specific, incredible speed, but a finite one nonetheless. This is the universe as we perceive it, the universe as our brains are wired to understand it, and indeed the universe as classical physics largely described it for centuries, from the gentle tug of gravity pulling an apple to the Earth, to the precisely calculated trajectory of a cannonball, to the whirring gears of a magnificent clockwork mechanism. The physical world seemed to operate on strict local principles. Every interaction had a point of contact. Every influence had to traverse the space between its source and its target. And nothing, absolutely nothing, could exert an influence instantaneously across a distance without some mediating force or particle making the journey. This principle of locality is so deeply ingrained in our understanding that we rarely even consider it. It's the silent assumption underpinning almost every action we take, every prediction we make about the physical world. It's why you don't worry about your car spontaneously teleporting to the moon when you start the engine, or about a conversation in your living room instantly being heard by someone in another country without the aid of technology. Our intuition screams that effects require direct physical causes, and those causes are always bound by the limits of space and time. For most of human history, this intuitive understanding served us incredibly well. It allowed us to build bridges, launch ships, predict the movements of the planets, and eventually construct the technological marvels that define our modern age. Isaac Newton's laws of motion and universal gravitation, formulated in the late 17th century, provided a mathematical framework for this local universe, while his concept of action at a distance for gravity was a point of philosophical contention. How could one body influence another without touching it? His equations worked. They predicted the orbits of planets with astonishing accuracy, and for practical purposes, the effect of gravity was still local. It was felt by objects in their immediate vicinity, even if the underlying mechanism wasn't fully understood. The gravitational influence, too, was thought to propagate at an infinite speed, but this was a subtle point, often overlooked in the face of its immense predictive power. Then came James Clerk Maxwell in the 19th century, with his groundbreaking equations of electromagnetism. Maxwell unified electricity and magnetism, demonstrating that light itself was an electromagnetic wave. Crucially, his equation showed that electromagnetic influences, changes in electric or magnetic fields, don't propagate instantaneously. They travel at a finite speed, the speed of light. If you flick a light switch, the electromagnetic field changes, and that change propagates outward at the speed of light. This was a profound confirmation of locality in the electromagnetic realm. It reinforced the idea that information and influence are always bound by a cosmic speed limit. So by the dawn of the 20th century, the picture of the universe seemed remarkably clear and consistent. It was a grand, predictable machine. Every part interacted with its neighbors, and signals traveled from point to point, always obeying the cosmic speed limit of light. If you knew the initial conditions of every particle, you could, in theory, predict the entire future of the universe. It was a universe of certainty, of billiard balls colliding and moving in perfect calculable paths. But this elegant, local, and intuitively satisfying picture, as robust as it seemed, contained tiny, almost imperceptible cracks. Cracks that would, over the next few decades, widen into chasms, revealing a reality so profoundly different, so utterly counterintuitive, that it would challenge our very understanding of existence. These cracks first appeared not in the grand movements of planets or the majestic sweep of light across the cosmos, but in the most minuscule, fundamental constituents of matter, in the bizarre and bewildering world of the atom. The strange behaviors observed at this microscopic scale couldn't be explained by our comfortable local understanding of the world. Energy didn't seem to flow smoothly, but in discrete packets, like tiny indivisible chunks. Particles sometimes behaved like waves, and waves sometimes behaved like particles, and perhaps most unsettling of all, measurements taken on these tiny entities didn't always yield predictable results. Sometimes they seemed inherently probabilistic, as if the universe itself was rolling dice. These were the first whispers that our intuitive, local universe, the one we experience every day, might be merely a surface phenomenon, a grand illusion built upon a deeper, more mysterious substrate. They were the first hints that something fundamental, something truly unsettling, was secretly connected, defying our most cherished notions of space, time, and independent reality. This journey into non-locality begins with the unraveling of that classical picture, with the dawning realization that the everyday world of locality, for all its predictability, is not the whole story. Indeed, it might be just the beginning of a much grander, more interconnected tale. The question we will explore is not just how things are connected, but why we've been blind to these connections for so long, and ultimately, is everything secretly connected? Prepare to have your most fundamental assumptions about reality gently but firmly shaken. The universe of billiard balls and perfect clockwork, the one where every action had a clear local cause, where every effect propagated at a finite speed, was a beautiful, elegant machine. For centuries, it served as our intellectual home, a comfortable framework for understanding the cosmos. But as the 20th century dawned, a series of increasingly bizarre observations, made not with telescopes gazing at distant stars, but with sophisticated instruments peering into the heart of matter itself, began to chip away at that comfortable certainty. It was like discovering that the gears of our grand cosmic clock weren't solid metal, but shimmering phantoms, sometimes there, sometimes not, sometimes spinning in multiple directions at once. Welcome then to the quantum realm, a place where our everyday intuition doesn't just bend, it shatters, and where the very notion of reality takes on a bewildering, fluid quality. The first hint that something was fundamentally amiss came not from a groundbreaking experiment, but from a theoretical puzzle: the problem of blackbody radiation. Imagine heating up an object, say a piece of metal. As it gets hotter, it starts to glow, first a dull red, then orange, then yellow, and eventually, if it gets hot enough, it emits white light. This glow is radiation, and physicists in the late 19th century were trying to describe mathematically how much radiation was emitted at different wavelengths for a given temperature. Classical physics, using all its elegant equations, predicted something ludicrous: that a hot object should emit an infinite amount of ultraviolet radiation, an outcome charmingly dubbed the ultraviolet catastrophe. Clearly, this wasn't happening, or we'd all be cooked by our toasters. It was Max Planck in 1900 who proposed a radical, almost desperate solution. What if energy wasn't continuous, like a ramp you could slide down at any point, but instead came in tiny, indivisible packets, or quanta? Imagine a staircase instead of a ramp. You can only stand on the steps, not in between them. Planck suggested that light energy was absorbed and emitted in these discrete bundles, each bundle having an energy proportional to its frequency. He even came up with a constant, Planck's constant, to describe the size of these bundles. It was a mathematical trick to make the equations work, and even Planck himself initially thought of it as a mere mathematical device, not a description of reality. He famously said, "I can't believe in the reality of the quanta themselves." But his trick worked, perfectly explaining the black-body radiation problem. The universe, it seemed, was quantized at its most fundamental level. Then came Albert Einstein, a few years later. In 1905, in what many consider his miracle year, he picked up Planck's radical idea and applied it to another puzzling phenomenon, the photoelectric effect. This was the observation that when light shines on certain metals, it can eject electrons, creating an electric current. But there were weird rules. Only light above a certain frequency, a certain color, could eject electrons, no matter how bright the light was. And if the light was above that threshold, electrons were ejected instantly, with no delay. Classical physics, which viewed light purely as a wave, couldn't explain this. A brighter wave should have more energy and eventually knock out electrons, regardless of color. But Einstein, taking Planck's quanta seriously, proposed that light itself was made of these little packets of energy, which he called light quanta, or photons. When a photon hits an electron, it's like one billiard ball hitting another. If the photon has enough energy, is of the right frequency/color, it can kick out an electron. If not, even a trillion low-energy photons won't do the trick. This revolutionary idea, that light traditionally thought of as a wave, also behaved like a particle, earned Einstein his Nobel Prize. It was the birth of wave-particle duality, the mind-bending concept that fundamental entities in the universe aren't simply waves or particles, but somehow exhibit characteristics of both, depending on how you look at them. This duality was extended to matter by Louis de Broglie in 1924, who hypothesized that particles like electrons could also behave like waves. This wasn't just a wild guess. It was later confirmed experimentally when scientists found that electrons could be diffracted and interfered with, just like waves. Imagine throwing tiny pebbles at a wall, and instead of bouncing off, they spread out like ripples in a pond. That's what electrons were doing. So now, everything was dual. Light could be particles, and particles could be waves. The clear, distinct lines of classical physics were blurring. The universe wasn't made of definitive, solid objects with precise locations and trajectories. It was a shimmering, probabilistic soup of wave particles. This brings us to the core of what makes the quantum realm so deeply unsettling to our everyday intuition: the concepts of superposition and probability. If a particle, like an electron, behaves like a wave, then it doesn't have a single, definite position. A wave is spread out over space. So, if an electron is a wave, where is it? Quantum mechanics says it's in a superposition of states, meaning it exists in multiple possible locations or states simultaneously, like a ghost haunting every corner of a room at once. It's not here or there, it's somehow both here and there, and everywhere in between, all at the same time. This is not a lack of knowledge on our part. It's a fundamental property of the particle itself. It's not until we measure its position that it seems to choose a single definite location. This leads to the infamous measurement problem and the bizarre idea that observation itself plays a role in shaping reality. Before measurement, the quantum world exists in a fuzzy, probabilistic haze of possibilities. Only upon interaction, upon observation, does one of those possibilities become concrete. Consider the famous thought experiment of Schrödinger's cat. Imagine a cat in a sealed box with a device that has a 50% chance of releasing a lethal poison, triggered by the decay of a single radioactive atom. According to quantum mechanics, until you open the box and observe it, The radioactive atom is in a superposition of both decayed and undecayed states. Therefore, the cat, linked to this quantum event, is in a superposition of being both alive and dead simultaneously. It's not that we don't know whether it's alive or dead, it's that in the quantum description it is both, until the act of observation forces it into one definite state. This isn't a mere philosophical musing, it's a consequence of the mathematical formalism of quantum mechanics, and it's a consequence that challenges our most basic understanding of reality. Objects don't just exist independently with definite properties, their properties are fluid and indeterminate until we interact with them. This inherent uncertainty isn't due to limitations of our instruments or our knowledge, it's built into the very fabric of the quantum world. This is encapsulated by Werner Heisenberg's uncertainty principle, formulated in 1927. It states that there are certain pairs of properties of a particle, like its position and its momentum, mass times velocity, that cannot both be known with perfect precision simultaneously. The more precisely you know one, the less precisely you can know the other. It's not that our measurement disturbs the particle, it's that the particle fundamentally doesn't have a precise position and a precise momentum at the same time. The sharp, clear edges of the classical world were replaced by a fundamental fuzziness. So the universe, at its most fundamental level, wasn't a predictable clockwork. It was a realm of probabilities, of particles that were also waves, of objects that could be in multiple places at once until observed. It was a place where certainty gave way to statistical likelihoods, and where the very act of looking seemed to solidify a fluid reality. This quantum world, born from the need to explain puzzling experimental results, was a triumph of prediction. Its equations consistently and accurately described the behavior of atoms, molecules, and light. But it was also a profound philosophical challenge. It replaced the comforting solidity of our everyday experience with a bewildering, counterintuitive strangeness. It hinted that the secret connections we seek might not be like threads tying together separate objects, but rather like the interwoven fabric of a single, probabilistic entity, where here and there and even now and then were far less distinct than our senses led us to believe. This perplexing new physics, often called quantum mechanics, provided the language for understanding the subatomic world, but it also opened the door to an even more unsettling possibility, that some connections might exist that defied even the quantum realm's already radical departure from locality. It prepared the ground for the most spooky revelation of all, the phenomenon of entanglement, which would push the boundaries of what we thought was possible even further. Possible if the revelations of quantum mechanics, the wave-particle duality, the probabilistic nature of reality, and the unsettling concept of superposition were a gentle shaking of our classical foundations, then the phenomenon known as entanglement was nothing short of an earthquake. It wasn't just about a particle being in multiple places at once, or the observer seemingly collapsing reality. Entanglement introduced an entirely new, deeply perplexing kind of connection, one that seemed to defy the very fabric of space and the speed limit of light. It was so profoundly unsettling that even Albert Einstein, the architect of relativity and the very person who helped birth quantum theory, famously described it as spooky action at a distance. And when Einstein, a man whose mind stretched the limits of human comprehension, found something spooky, you knew you were onto something truly extraordinary. Imagine for a moment 2 coins. These aren't ordinary coins, these are quantum coins. And before we flip them, they are in a special, entangled state. This means that if one coin lands on heads, the other must land on tails, and vice versa. There's a perfect correlation. Now here's where it gets weird. In the quantum world, before you actually flip either coin, each coin doesn't have a definite state of heads or tails. Each one is in a superposition of being both heads and tails simultaneously. They are undefined. But the moment you flip one coin, say the first one, and it lands on heads, instantaneously, the other coin, even if it's light years away, instantly collapses into the state of tails. There's no time delay. There's no signal sent between them. It's as if they are inextricably linked, not by any physical connection we can observe, but by some unseen fundamental bond that transcends the vast expanse of space. This is the essence of entanglement. It describes a situation where two or more quantum particles become correlated in such a way that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by large distances. They are born together, interact briefly, and then fly apart, yet they remain intimately linked, their destinies intertwined, no matter how far they roam. When you measure a property of one entangled particle, say its spin or its polarization, you instantaneously know the corresponding property of its entangled partner without ever having to look at the second particle. It's as if their individual probabilities are linked, such that when one probability collapses into a definite outcome, the other's probability immediately follows suit, ensuring their correlated fates. The concept first truly began to bother physicists in the 1930s. Erwin Schrödinger, one of the pioneers of quantum mechanics, was the first to coin the term entanglement, or Verschränkung in German, and he saw it as the defining characteristic of quantum mechanics, but also as its most puzzling feature. He wrote, "When two systems, of which we know the states by their respective representatives, enter into temporary physical interaction due to known forces between them, and when after a time of mutual influence the systems separate again, then they can no longer be described in the same way as before, viz. by assigning to each of them a representative of its own. I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought." He recognized that this non-separable nature was truly revolutionary, but it was Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, who truly sharpened the paradox in their famous 1935 paper, often referred to as the EPR paradox. They didn't like entanglement. They argued that quantum mechanics, with its probabilistic outcomes and spooky action, must be incomplete. Their argument was based on what they called local realism. Realism suggests that physical properties have definite pre-existing values, whether we measure them or not. Think of our coins. They are either heads or tails, even if we don't know it yet. Locality suggests that distant events cannot instantaneously influence each other. Information, as established by Einstein himself in his theory of special relativity, cannot travel faster than the speed of light. The EPR paradox went something like this. If you have two entangled particles, A and B, and you measure a property of particle A, you instantly know the corresponding property of particle B, no matter how far away B is. If realism is true, then particle B must have already had that property before you measured A. If locality is true, then your measurement of A cannot instantaneously influence B. Therefore, Einstein, Podolsky, and Rosen concluded that quantum mechanics must be incomplete because it didn't account for these pre-existing, hidden variables that would determine the outcome of B's measurement without any spooky action. They believed there must be some deeper, as yet undiscovered classical theory that would explain these correlations through local interactions, perhaps some hidden information shared between the particles at the moment they were created, information that then dictated their future outcomes without any instantaneous communication. To them, the spooky action was an indication of a flaw in the quantum description, not a fundamental feature of reality. They were strong advocates for a universe where properties were real and predetermined, and where influence was always local. The debate simmered for decades. It was a fascinating philosophical argument, but largely untestable. How could you definitively prove whether the particles had hidden variables, or if genuine spooky action was at play? It seemed an intractable problem, confined to the theoretical blackboard and the halls of academia. The core of the problem was this: could quantum mechanics, with its probabilistic outcomes and non-local correlations, be explained by a more fundamental, deterministic theory governed by local hidden variables, that is, properties that were predetermined at the moment of interaction but unknown to us, and which acted locally? If such a theory existed, there would be no spooky action, just a lack of information on our part. The stage was set for a scientific revolution, not just through theoretical brilliance, but through audacious experimental design. The challenge was immense: how to distinguish between true quantum non-locality and the possibility of some sophisticated, but ultimately local prearrangement. This was the profound question that hung over physics, a question that hinted at the very nature of reality itself. Was the universe fundamentally interconnected in a way that defied our most cherished principles, or was there simply a deeper, more classical layer of reality waiting to be uncovered? The answer, when it finally arrived, would come not from another philosophical debate, but from a brilliant conceptual leap that would allow for a direct, undeniable test of Einstein's spooky action. It would reveal that the universe was indeed far stranger and far more deeply connected than even the greatest minds had dared to believe. The whispers of hidden connections were about to become an undeniable roar, echoing across the vast distances of the cosmos. The debate ignited by Einstein, Podolsky, and Rosen in their 1935 paper simmered for decades, a tantalizing philosophical standoff. On one side stood Einstein, a giant of physics, advocating for a universe of local realism, where properties were inherent and influences were confined by the speed of light. On the other, the perplexing predictions of quantum mechanics, hinting at a universe of deep, instantaneous connections, spooky action at a distance. It was a clash between intuition and the seemingly absurd mathematics of the quantum world, a battle of titans with no clear winner, no definitive experiment that could say this one is right and that one is wrong. The problem was, how could you possibly distinguish between a pre-existing, hidden correlation and a genuinely instantaneous, non-local connection? How could you design an experiment that would definitively test the difference between particles that knew their fates beforehand and particles that only decided their fates the moment one of them was observed, instantly influencing its distant twin? Bell's genius lay in his ability to translate this abstract philosophical argument into a concrete, testable mathematical inequality. He realized that if local hidden variables did exist, they would place a fundamental limit on how strongly correlated the measurements of two entangled particles could be. Imagine our entangled coins again. If their outcomes were secretly predetermined by hidden instructions given to them at their creation, then there would be certain statistical patterns that their results would have to obey, no matter what. Bell's theorem, often expressed as Bell's inequality, mathematically quantified these limits. It showed that if reality was governed by local hidden variables, if there was no spooky action and everything was predetermined locally, then the correlations between measurements on entangled particles could not exceed a certain statistical bound. However, if quantum mechanics, with its genuine non-local connections, was correct, then these correlations could be stronger than what any local hidden variable theory would allow. The breakthrough, remarkably, came not from another eminent quantum physicist working in a grand laboratory, but from a relatively unsung hero, an Irish physicist named John Stuart Bell, working at CERN in the 1960s. Bell, unlike many of his contemporaries who were content to shut up and calculate and simply accept quantum mechanics for its predictive power, was deeply bothered by the philosophical implications of the EPR paradox. He wasn't satisfied with simply saying, "That's just how quantum mechanics works." He wanted to know why it worked that way, and whether Einstein's concerns about hidden variables were valid. The locality loophole was concerned with the possibility that the two measurement stations for the entangled particles were not truly causally disconnected. Could there be a tiny sub-light speed signal traveling between them during the measurement process, influencing the second measurement based on the first? To close this, the measurements needed to be performed so rapidly, and the detectors so far apart, that no signal traveling at or below the speed of light could possibly communicate the first measurement's outcome to the second particle before its own measurement was complete. This required splitting the particles, sending them to different locations, and then performing the measurements almost simultaneously, with the decision of which measurement to make being taken randomly and very quickly. It was a brilliant, almost deceptively simple idea. Bell didn't try to explain how entanglement worked. He simply devised a way to experimentally test whether it was a product of local hidden variables or something genuinely non-local. He created a benchmark. If experimental results violated Bell's inequality, it would mean that local realism was false. It would mean that either locality was wrong, or realism was wrong, or both. And given the overwhelming evidence for realism in our macroscopic world, the primary implication was that locality, at the quantum level, was not upheld. It was a profound challenge to our understanding of the universe. The stage was now set for the experimentalists. The first truly significant Bell test experiments were conducted in the early 1970s by John Clauser and Stuart Friedman. They used entangled photons and measured their polarizations. Their early results indicated a violation of Bell's inequality, supporting quantum mechanics, but they were still somewhat limited by technological constraints and potential loopholes. These loopholes were theoretical avenues through which a local hidden variable theory might still sneak in an explanation. The most significant of these were the locality loophole and the detection loophole. The debate ignited by Einstein, Podolsky, and Rosen in their 1935 paper simmered for decades, a tantalizing philosophical standoff. On one side stood Einstein, a giant of physics, advocating for a universe of local realism, where properties were inherent and influences were confined by the speed of light. On the other, the perplexing predictions of quantum mechanics, hinting at a universe of deep, instantaneous connections, spooky action at a distance. It was a clash between intuition and the seemingly absurd mathematics of the quantum world, a battle of titans with no clear winner, no definitive experiment that could say this one is right and that one is wrong. The problem was, how could you possibly distinguish between a pre-existing, hidden correlation and a genuinely instantaneous, non-local connection? How could you design an experiment that would definitively test the difference between particles that knew their fates beforehand and particles that only decided their fates the moment one of them was observed, instantly influencing its distant twin? The breakthrough, remarkably, came not from another eminent quantum physicist working in a grand laboratory, but from a relatively unsung hero, an Irish physicist named John Stuart Bell, working at CERN in the 1960s. Bell, unlike many of his contemporaries who were content to shut up and calculate and simply accept quantum mechanics for its predictive power, was deeply bothered by the philosophical implications of the EPR paradox. He wasn't satisfied with simply saying, "That's just how quantum mechanics works." He wanted to know why it worked that way, and whether Einstein's concerns about hidden variables were valid. Bell's genius lay in his ability to translate this abstract philosophical argument into a concrete, testable mathematical inequality. He realized that if local hidden variables did exist, they would place a fundamental limit on how strongly correlated the measurements of two entangled particles could be. Imagine our entangled coins again. If their outcomes were secretly predetermined by hidden instructions given to them at their creation, then there would be certain statistical patterns that their results would have to obey, no matter what. Bell's theorem, often expressed as Bell's inequality, mathematically quantified these limits. It showed that if reality was governed by local hidden variables, if there was no spooky action and everything was predetermined locally, then the correlations between measurements on entangled particles could not exceed a certain statistical bound. However, if quantum mechanics, with its genuine non-local connections, was correct, then these correlations could be stronger than what any local hidden variable theory would allow. It was a brilliant, almost deceptively simple idea. Bell didn't try to explain how entanglement worked. He simply devised a way to experimentally test whether it was a product of local hidden variables or something genuinely non-local. He created a benchmark. If experimental results violated Bell's inequality, it would mean that local realism was false. It would mean that either locality was wrong, or realism was wrong, or both. And given the overwhelming evidence for realism in our macroscopic world, the primary implication was that locality, at the quantum level, was not upheld. It was a profound challenge to our understanding of the universe. The stage was now set for the experimentalists. The first truly significant Bell test experiments were conducted in the early 1970s by John Clauser and Stuart Friedman. They used entangled photons and measured their polarizations. Their early results indicated a violation of Bell's inequality, supporting quantum mechanics, but they were still somewhat limited by technological constraints and potential loopholes. These loopholes were theoretical avenues through which a local hidden variable theory might still sneak in an explanation. The most significant of these were the locality loophole and the detection loophole. The locality loophole was concerned with the possibility that the two measurement stations for the entangled particles were not truly causally disconnected. Could there be a tiny sub-light speed signal traveling between them during the measurement process, influencing the second measurement based on the first? To close this, the measurements needed to be performed so rapidly and the detectors so far apart that no signal traveling at or below the speed of light could possibly communicate the first measurement's outcome to the second particle before its own measurement was complete. This required splitting the particles, sending them to different locations, and then performing the measurements almost simultaneously, with the decision of which measurement to make being taken randomly and very quickly. The detection loophole related to the efficiency of the detectors. If the detectors weren't perfectly efficient, and only a small subset of the entangled particles were actually measured, it was possible that the measured subset wasn't representative of all the entangled pairs. Perhaps the unmeasured particles were behaving exactly as a local hidden variable theory would predict, and only the measured ones by chance showed quantum correlations. To close this, experimenters needed very high efficiency detectors that could detect a vast majority of the entangled pairs. Enter Alain Aspect and his team in Paris in the early 1980s. Aspect's experiments were a landmark achievement. He significantly improved upon Clauser's work by introducing rapidly switching measurement directions for the entangled photons. His setup involved sending entangled photons in opposite directions to two detectors, each equipped with a fast switching mechanism that could randomly choose between two different polarization measurement settings while the photons were in flight. This was crucial for closing the locality loophole. By making the choice of measurement setting truly random and fast enough that light couldn't travel between the two detectors during the measurement process, Aspect definitively ruled out any local communication between the particles or the measurement devices. His results showed a clear and undeniable violation of Bell's inequality, strongly supporting quantum mechanics and refuting local hidden variable theories. Einstein's spooky action was looking less like an argument for an incomplete theory and more like a fundamental, if baffling, feature of reality. Still, a few subtle loopholes remained open. But over the ensuing decades, a new generation of experimentalists, leveraging incredible technological advancements, systematically closed them. Anton Zeilinger's group in Vienna, for example, pioneered techniques for creating and manipulating entangled particles, pushing the boundaries of Bell tests. In the 2010s, several groups around the world, notably those led by Ronald Hansen in Delft, Anton Zeilinger in Vienna, and John Clauser himself, who had been instrumental in the early tests, performed what are often referred to as loophole-free Bell tests. These experiments pushed the detectors kilometers apart, sometimes using fiber optic cables or even beaming entangled photons to separate buildings. They incorporated truly random number generators, often based on cosmic signals or quantum vacuum fluctuations, to determine measurement settings, eliminating any possibility of pre-programming, and they achieved unprecedented detection efficiencies. The results were unequivocal. In every single one of these rigorous loophole-free experiments, Bell's inequality was violated, consistently, repeatedly. This was not a fluke or an anomaly. It was a clear statistical signal that the universe, at its fundamental level, does not operate according to local realism. This meant that either reality is not local, or it is not real in the sense of having definite properties independent of measurement. Given that the concept of realism, that things exist whether we look at them or not, is so fundamental to our everyday experience, the vast majority of physicists interpret these results as a definitive rejection of locality in the quantum realm. What does this mean? It means that spooky action at a distance isn't spooky in the sense of being a flawed concept. It's spooky because it's real. The entangled particles, no matter how far apart, behave as a single, indivisible quantum system. The measurement of one instantaneously influences the state of the other, not through a signal, but through some deeper, non-local connection that defies our classical understanding of space and time. It implies that separation in space, at the deepest quantum level, might not be as fundamental as we perceive it to be. The universe isn't a collection of independent entities interacting locally. It's a vast, interconnected web where information about one part can be instantaneously reflected in another, no matter the distance. The philosophical debate had moved from the realm of thought experiments to the undeniable clarity of experimental data. The universe had spoken, and its message was clear. Everything isn't just locally connected. There are deeper, secret threads weaving through the fabric of reality, threads that tie distant quantum particles together in an unbreakable, instantaneous dance. This profound revelation opened a Pandora's box of questions, not just about the nature of subatomic particles, but about the very essence of space, time, and causality itself. The implications were, and continue to be, staggering. The experimental confirmation of non-locality, particularly through the groundbreaking Bell test experiments, sent shockwaves through the scientific community and eventually into popular culture. The phrase "spooky action at a distance" became a tantalizing shorthand for something truly revolutionary, something that defied the seemingly immutable laws of the universe. For many, it conjured images of instant communication across vast cosmic distances, of psychic powers, or even of a hidden ethereal force dictating the fate of the cosmos. The temptation to leap to sensational conclusions, to fill the void of the unknown with fantastical notions, is powerful. But in the realm of science, especially when dealing with concepts as counterintuitive as quantum mechanics, it's crucial to distinguish between what the evidence truly tells us and what our imaginations might wish it to be. So, before we delve further into the profound implications of non-locality, it's absolutely vital to clarify what non-locality isn't. Dispelling these common myths is just as important as understanding the science itself, for misinterpretations can lead to pseudoscience and a distortion of the incredible truths that quantum physics has actually uncovered. The most pervasive, and perhaps most appealing misconception about non-locality is that it allows for faster-than-light communication. Imagine if you could instantly send a message to a distant galaxy. No more waiting for light to travel for millions of years. You could have a real-time conversation with extraterrestrial life. This sounds like science fiction, and indeed it is. Despite the instantaneous correlation observed between entangled particles, non-locality does not permit the transmission of information faster than the speed of light. This is a crucial point, and it's often the most difficult one for people to grasp. Let's revisit our entangled coins. When you flip the first coin, and it instantly reveals heads, its distant entangled partner instantaneously becomes tails. It seems like you've sent a signal, right? You knew the distant coin's state without any delay, but here's the catch. You don't know what the first coin will be until you flip it. Its outcome is fundamentally probabilistic. You can't choose whether it lands heads or tails. It's truly random. So while you know the state of the distant coin after you measure the first one, you can't use that instantaneous knowledge to send a predetermined message. If you wanted to send a message like "hello," you'd need to encode it in a sequence of heads and tails. But because the outcome of each flip is random, you can't control it. The best you could do is produce a random stream of information, which is meaningless to anyone receiving it without a pre-agreed code. There's no way to impose your will or a specific message onto the initial random outcome of the first measurement. The correlation is there, but the ability to control that correlation for communication is not. This constraint is deeply rooted in the principles of quantum mechanics and Einstein's theory of special relativity. If faster-than-light communication were possible, it would immediately break causality, meaning effects could precede their causes. You could send a message back in time, for instance, which would lead to all sorts of logical paradoxes. The universe, despite its quantum weirdness, appears to uphold causality. The instantaneous correlation in entanglement isn't about information transfer in the classical sense. It's about the collapse of a shared, probabilistic quantum state. The particles are a single, extended system, and when one part of that system resolves its uncertainty, the other part instantly reflects that resolution. But it's a resolution of an inherent randomness that you cannot manipulate. Another significant myth is that non-locality implies telekinesis, psychic powers, or other forms of magic. The allure of a secret connection can easily lead to the belief that thoughts or intentions can directly influence distant objects or people. This is absolutely not what quantum non-locality describes. Quantum entanglement deals with specific, measurable physical properties of subatomic particles, like spin, polarization, or energy levels. It operates under precise mathematical rules and has been verified by rigorous scientific experiments. There's no scientific basis, none whatsoever, for linking quantum entanglement to consciousness, psychic abilities, or any form of supernatural phenomenon that would allow for direct mental control over matter or information transfer through willpower alone. While some fringe theories or popular science interpretations might try to bridge this gap, they do so without empirical support and often misrepresent the fundamental nature of quantum mechanics. The spooky action is a property of the quantum vacuum and its fundamental excitations, not of minds or spirits. It's a physical phenomenon, not a metaphysical one, and it operates within the strict, albeit strange, boundaries of physics. Furthermore, non-locality isn't about deterministic hidden variables. This is precisely what Bell's theorem disproved. Einstein and his colleagues hypothesized that entangled particles did have predetermined properties, hidden variables, which would explain their correlations without any instantaneous influence. But Bell's inequality showed that if such local deterministic hidden variables existed, the correlations observed in experiments could not be as strong as quantum mechanics predicts, and as experiments have confirmed. The violation of Bell's inequality tells us that the particle's properties are not merely predetermined in a local way. Their outcomes are fundamentally probabilistic, and their correlations arise from a non-local, instantaneous connection, not from a secret classical instruction set given to them at birth. So non-locality doesn't mean the universe is secretly more predictable or classically deterministic than we thought. It means it's less so in certain ways, and its connections are even more profound and counterintuitive than a simple prearrangement. It's also crucial to understand that non-locality doesn't mean all particles are constantly entangled with each other. While entanglement is a fundamental quantum phenomenon, it's also a fragile one. Entangled states are very susceptible to decoherence, which is the process by which a quantum system loses its quantum properties and begins to behave classically due to interaction with its environment. Imagine a delicate quantum entanglement as a perfectly balanced house of cards. Even the slightest breeze, interaction with the environment, can cause it to collapse into a more stable, classical configuration. This is why we don't observe everyday objects like baseballs or chairs existing in superpositions or entangled states. They are constantly interacting with countless particles in their environment, air molecules, photons, gravity, causing them to decohere almost instantly. The macroscopic world we inhabit appears classical and local, precisely because of this continuous interaction and decoherence. The quantum weirdness is typically confined to isolated microscopic systems. So when we talk about non-locality, we are talking about a specific, verifiable quantum phenomenon, where quantum systems, having once interacted, retain a probabilistic link that transcends space. We are not talking about magic, psychic powers, or a cosmic internet. We are talking about a fundamental aspect of reality, rigorously proven by experiments, that challenges our deepest assumptions about independence and separation. It tells us that the universe is interconnected in a way that is utterly foreign to our everyday experience, a connection that is real, instantaneous, and yet cannot be exploited for communication. It's a subtle, profound truth, one that forces us to expand our understanding of what connected truly means, moving beyond simple cause and effect to a deeper, more unified quantum reality. The implications of this established truth are, if anything, far more fascinating than any sensationalized myth, for they force us to confront the very nature of existence itself. The journey through the quantum realm has, so far, primarily focused on the enigmatic behavior of individual particles, photons, electrons, and the like. We've grappled with their probabilistic existence, their simultaneous presence in multiple states, and the startling, experimentally verified reality of entanglement, a spooky action that links distant particles instantaneously. This revelation alone is enough to dismantle our comfortable, classical notions of a purely local universe. But what if non-locality isn't just a quirk of the subatomic world, a strange dance performed by tiny, isolated quantum objects? What if these secret connections extend far beyond individual particles, reaching into the very structure of space and time, the fundamental canvas upon which our universe is painted? This is where the exploration of non-locality becomes even more profound, moving from the microscopic to the potentially cosmic, suggesting that the very fabric of reality might be woven with non-local threads. To truly appreciate this possibility, we need to broaden our understanding of what particles actually are in the quantum world. In the classical view, particles are discrete, tiny billiard balls. But in quantum mechanics, and particularly in a more advanced framework known as quantum field theory, QFT, the picture is far more nuanced. QFT doesn't view particles as fundamental entities bouncing around. Instead, it posits that the universe is permeated by various fundamental fields. There's an electron field, a photon field, a quark field, and so on, for every type of fundamental particle. What we perceive as a particle is actually an excitation, a localized ripple or vibration in its corresponding field, much like a ripple in a pond, isn't a separate entity, but an excitation of the water itself. So an electron isn't a tiny ball. It's a localized excitation of the electron field that stretches throughout all of space. A photon is a quantized excitation of the electromagnetic field. This field-theoretic perspective has been incredibly successful, forming the bedrock of the standard model of particle physics, which describes all known fundamental particles and forces, except gravity. And crucially for our discussion, entanglement, which we previously discussed in terms of individual particles, is an intrinsic and pervasive feature of these quantum fields themselves. When two particles, i.e. field excitations, become entangled, it's not just a connection between two separate billiard balls. It's a deep correlation between localized excitations within a single, continuous, non-local quantum field. The non-locality of entangled particles is therefore a direct manifestation of the underlying non-local nature of the quantum fields that constitute them. This shifts our perspective dramatically. It means that non-locality isn't merely about distant objects being linked. It's about the underlying fields that give rise to those objects being inherently connected across vast distances. If you disturb the electron field in one location, its effects, however subtle, are instantaneously correlated with changes in the field across the universe through the mechanism of entanglement. While these correlations cannot be used for faster-than-light communication, they indicate that the vacuum of space itself, filled with these omnipresent quantum fields, is a sea of potential and interconnectedness, a cosmic web of probabilistic relationships. The emptiness of space, as classical physics conceived it, is in fact teeming with quantum activity, constantly fluctuating, generating and annihilating virtual particles, and all of this is subject to the rules of quantum non-locality. This deep integration of non-locality within quantum field theory naturally leads to even more speculative, yet profoundly important questions when we consider the ultimate frontier of physics, quantum gravity. Our two most successful theories of the universe, quantum mechanics, which describes the very small, and general relativity, which describes gravity and the very large, space, time, and the universe as a whole, are currently incompatible. General relativity describes space-time as a smooth, continuous fabric that can be warped by mass and energy, creating gravity. Quantum mechanics, as we've seen, describes reality as quantized, probabilistic, and fundamentally non-local at its deepest level. Reconciling these two theories, creating a theory of quantum gravity, is the holy grail of modern physics. And many leading candidates for quantum gravity theories, such as string theory and loop quantum gravity, suggest that space-time itself might not be the continuous, smooth entity we perceive. Instead, space-time might be emergent, built from discrete quantum atoms or loops, or even be a manifestation of a deeper, higher dimensional reality. If space-time itself is quantum, then it stands to reason that it too might exhibit quantum properties, including non-locality. Imagine if the very fabric of space and time were entangled. What would that even mean? It could imply that points in space-time that appear vastly distant to us are at a more fundamental level intimately connected through quantum entanglement. Some theories, like certain interpretations of holographic principle in quantum gravity, suggest a deep connection between gravity and entanglement. For instance, the EREPR conjecture, proposed by Leonard Susskind and Juan Maldacena, speculates that if two black holes are maximally entangled EPR, then they are connected by a wormhole. ER stands for Einstein-Rosen bridge. This is a highly speculative but fascinating idea that directly links the most spooky feature of quantum mechanics to the most mind-bending feature of general relativity. It suggests that entanglement isn't just happening in space-time, but that it might be constituting space-time itself, or at least intimately connected to its very geometry. If space-time itself is non-local, then our perception of distinct locations and finite distances might be an emergent, classical approximation of a deeper interconnected reality. The cosmic distances we measure, the vast emptiness between galaxies, might, at a more fundamental quantum level, be bridged by the instantaneous threads of non-locality. It doesn't mean we can teleport across the universe, but it means the underlying structure of reality might be far more unified and less fractured than our everyday experience suggests. The universe, in this view, is not a collection of separate objects inhabiting a pre-existing space, but rather a single, indivisible quantum entity where space and time are themselves consequences of the quantum connections within it. This is the frontier of current research, still very much in the realm of theoretical speculation and mathematical exploration rather than experimental verification. But the consistent observation of non-locality at the particle level and its inherent presence in quantum field theory provides a powerful impetus to explore how these non-local principles might scale up to the cosmic level. The universe, it seems, is not merely a collection of isolated parts. It is a grand entangled tapestry where the threads of connection run deeper than we ever imagined, perhaps even weaving together the very dimensions in which we exist. The more we probe the quantum foundations of reality, the more we find that the separation we perceive is, in a profound sense, an illusion. The secret connections are not just between particles, but potentially within the very essence of the space and time that define our universe, that define the quantum realm, with its bizarre probabilities, its shimmering superpositions, and its undeniable non-local connections, forces us to question the very nature of reality. It's a world where the act of observation seems to play a fundamental role, collapsing a wave of possibilities into a single, concrete outcome. This peculiar feature, often called the measurement problem, has led some to ask perhaps the most audacious and controversial question of all. Could consciousness itself be intertwined with quantum phenomena? And might it, in turn, exhibit non-local properties? This is a treacherous terrain, where scientific rigor often gives way to philosophical speculation, and where the line between proven physics and tantalizing hypothesis becomes exceptionally blurred. Yet, it's a question that continues to fascinate, precisely because it grapples with two of the universe's greatest mysteries, the nature of quantum reality and the enigma of the human mind. One of the most prominent and ambitious, though highly controversial theories, attempting to link consciousness to quantum processes and potentially to non-locality, is the orchestrated objective reduction or theory, proposed by the physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their hypothesis suggests that consciousness arises not from classical neuronal firings alone, but from quantum computations occurring within structures called microtubules inside our brain neurons. Microtubules are protein polymers that form part of the cell's cytoskeleton, involved in cell structure and transport. Penrose and Hameroff proposed that these microtubules can maintain quantum superpositions and entanglement for brief periods, and that consciousness emerges from sequences of orchestrated objective reductions, ORS. They suggest that these collapses are not random, but orchestrated by an unknown, possibly non-local influence from fundamental space-time geometry at the Planck scale, the smallest possible scale of the universe. Let's revisit the measurement problem. In the standard interpretation of quantum mechanics, the quantum system exists in a superposition of all its possible states until it is measured or observed. At that point, the superposition collapses, and the system settles into one definite state. But what exactly constitutes a measurement? Is it the interaction with a detector? Is it the information being processed by a classical computer? Or does it require a conscious observer? For decades, physicists have debated this. Many argue that any interaction with a macroscopic environment, including a measuring device, causes the superposition to decohere and effectively collapse. They say consciousness isn't needed, it's just physics. However, other interpretations, particularly those that lean towards the idea that consciousness is fundamental, suggest that only a conscious mind can truly collapse the quantum wave function, turning possibility into actuality. This is often an appealing idea, as it grants consciousness a profound, active role in shaping reality, moving it from a mere byproduct of brain activity to a central player in the cosmic drama. The quantum realm, with its bizarre probabilities, its shimmering superpositions, and its undeniable non-local connections, forces us to question the very nature of reality. It's a world where the act of observation seems to play a fundamental role, collapsing a wave of possibilities into a single, concrete outcome. This peculiar feature, often called the measurement problem, has led some to ask perhaps the most audacious and controversial question of all. Could consciousness itself be intertwined with quantum phenomena, and might it in turn exhibit non-local properties? This is a treacherous terrain, where scientific rigor often gives way to philosophical speculation, and where the line between proven physics and tantalizing hypothesis becomes exceptionally blurred. Yet, it's a question that continues to fascinate, precisely because it grapples with two of the universe's greatest mysteries, the nature of quantum reality and the enigma of the human mind. Let's revisit the measurement problem. In the standard interpretation of quantum mechanics, the quantum system exists in a superposition of all its possible states until it is measured or observed. At that point, the superposition collapses, and the system settles into one definite state. But what exactly constitutes a measurement? Is it the interaction with a detector? Is it the information being processed by a classical computer? Or does it require a conscious observer? For decades, physicists have debated this. Many argue that any interaction with a macroscopic environment, including a measuring device, causes the superposition to decohere and effectively collapse. They say consciousness isn't needed, it's just physics. However, other interpretations, particularly those that lean towards the idea that consciousness is fundamental, suggest that only a conscious mind can truly collapse the quantum wave function, turning possibility into actuality. This is often an appealing idea, as it grants consciousness a profound, active role in shaping reality, moving it from a mere byproduct of brain activity to a central player in the cosmic drama. One of the most prominent and ambitious, though highly controversial theories, attempting to link consciousness to quantum processes and potentially to non-locality, is the orchestrated objective reduction or theory, proposed by the physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their hypothesis suggests that consciousness arises not from classical neuronal firings alone, but from quantum computations occurring within structures called microtubules inside our brain neurons. Microtubules are protein polymers that form part of the cell's cytoskeleton, involved in cell structure and transport. Penrose and Hameroff proposed that these microtubules can maintain quantum superpositions and entanglement for brief periods, and that consciousness emerges from sequences of orchestrated objective reductions, ORs. They suggest that these collapses are not random, but orchestrated by an unknown, possibly non-local influence from fundamental space-time geometry at the Planck scale, the smallest possible scale of the universe. The objective reduction part of their theory is Penrose's idea that the superposition eventually collapses due to inherent instabilities in space-time at the quantum gravitational level, even without an external observer. The orchestrated part is Hameroff's contribution, proposing that these objective reductions are synchronized or orchestrated across various microtubules due to factors like synaptic inputs and post-translational modifications of tubulin. In this highly speculative framework, moments of consciousness are likened to discrete quantum events, self-collapses of superposed states within the brain's quantum machinery. If all were true, and if these quantum processes within the brain truly involve entanglement, then it opens a door, albeit a very narrow and speculative one, to the idea of non-local aspects of consciousness. If consciousness is fundamentally quantum mechanical and involves entangled states, then perhaps, in some incredibly subtle and indirect way, different conscious minds could be non-locally linked, or even that consciousness itself could transcend the boundaries of individual brains. Some proponents of this idea hint at the possibility of shared consciousness, collective unconsciousness, or even survival of consciousness after death, all based on the quantum nature of reality. They might suggest that if the self is rooted in non-local quantum processes, then the ordinary boundaries of self might not be as rigid as we perceive. However, it is absolutely essential to approach these ideas with extreme caution and a strong dose of scientific skepticism. The Or theory, while intellectually fascinating and supported by the formidable intellects of Penrose and Hameroff, faces immense challenges and is not widely accepted by the mainstream neuroscience or physics communities. The primary objections are manifold. Firstly, the brain is a warm, wet, noisy environment. Quantum states, particularly entanglement, are incredibly fragile and prone to decoherence, the process by which they lose their quantum properties almost instantaneously through interaction with the environment. Maintaining coherent quantum states within the hot, complex, and rapidly interacting environment of a living brain for any biologically relevant period of time is considered extraordinarily difficult, if not impossible, by most physicists. The timescales involved in neuronal activity are far, far longer than the fleeting moments over which quantum coherence is typically maintained in controlled laboratory settings, even at extremely low temperatures. Secondly, there is currently no direct experimental evidence whatsoever to support the existence of macroscopic quantum coherence or entanglement within the brain, let alone its role in consciousness. While quantum effects are undeniably at play at the molecular level in biological processes like photosynthesis or enzyme catalysis, extending these effects to complex brain-wide phenomena like consciousness remains highly speculative and unproven. The specific claims of O, such as the mechanism of objective reduction at the Planck scale, are themselves deeply rooted in unverified theories of quantum gravity. Despite the lack of empirical evidence and the strong theoretical objections, the exploration of consciousness and non-locality continues to be a vibrant area of discussion, albeit largely on the fringes of mainstream science. The allure is understandable if quantum mechanics challenges our very notion of reality, and if consciousness is itself a mystery, then perhaps the solution to one lies in the other. It taps into a deep human desire for interconnectedness, for a universe where our minds are not just isolated chemical machines, but a part of a grander, perhaps even non-local, cosmic tapestry. For now, the scientific consensus remains that consciousness is an emergent property of complex neuronal networks and their classical interactions, albeit a property we still don't fully understand. While the idea of quantum effects playing a role in consciousness remains a tantalizing what-if, and while the non-local nature of reality is indeed profound, linking the two directly to explain the measurement problem or to infer extraordinary mental capabilities remains firmly in the realm of hypothesis. It serves as a reminder that while quantum non-locality is an established truth of physics, we must be careful not to extrapolate it beyond its proven boundaries. The secret connections in the universe are real, but they are defined by the rigorous laws of physics, not by our hopes for extraordinary powers or our desire to explain all mysteries with a single sweeping speculative theory. The mystery of consciousness and the reality of non-locality are both profound, but whether they are directly linked in this deeply entangled way remains a question for future scientific inquiry, not a current conclusion. If non-locality challenges our fundamental understanding of space, binding distant points with instantaneous, mysterious connections, then it's perhaps inevitable that it also forces us to re-examine our most intuitive, yet least understood dimension: time. Our everyday experience of time is relentlessly linear, a one-way street flowing from a fixed past, through a fleeting present, into an uncertain future. Cause precedes effect. The past is done, the future is yet to be determined. But the quantum realm, particularly through the lens of non-locality, hints at a far more fluid, interconnected temporal landscape, where the usual arrow of time might not always be so clear, and where the past, present, and future might be more entangled than we ever conceived. The very instantaneousness of entanglement, the spooky action, immediately raises questions about causality and the flow of time. If measuring particle A instantly influences particle B, even light years away, does that imply a violation of the speed of light, and by extension, a challenge to the fixed sequence of events? As we discussed, this doesn't allow for faster-than-light information transfer, which preserves the macroscopic arrow of causality. You can't send a message to the past. However, the fundamental correlation itself, the fact that two distant events are undeniably linked without any time delay, suggests a deeper synchronicity that doesn't fit neatly into our linear notions of before and after when considering the quantum state itself. The particles are a single, indivisible system, and their shared fate is established, in some sense, simultaneously across all of space-time. This leads to some truly mind-bending concepts, one of the most provocative being retrocausality. This isn't a mainstream idea in physics, and it's deeply contentious, but it surfaces in some interpretations of quantum mechanics when grappling with non-locality. Retrocausality suggests that future events could, in some subtle way, influence past events. For instance, in an entanglement experiment, imagine a particle, A, is measured at time t, and its entangled partner, B, is measured at time t, per 20. The standard view is that Anne's measurement collapses the superposition for both A and B at t. But a retrocausal interpretation might suggest that the choice of measurement setting for being at t
20
could, in some sense, influence the properties of a back at time. This isn't about sending information back in time to change history. It's about the fundamental properties of particles being established in a non-local way across time, as well as space. One popular model that often intersects with these ideas is the transactional interpretation of quantum mechanics proposed by John Cramer. In this interpretation, a quantum event, like an electron emitting a photon, is viewed as a transaction occurring between the emitter and the absorber, which involves both a retarded wave moving forward in time and an advanced wave moving backward in time. These waves meet and form a transaction in space-time, defining the quantum event. While abstract, it suggests that quantum correlations, including entanglement, might arise from a handshake between past and future, implying a form of communication that transcends the linear flow of time. This is a very different way of looking at causality, one where the universe isn't just evolving forward, but where the outcomes of future events are, in a very subtle quantum sense, already influencing the probabilities of past choices. The implications of non-locality for time also find resonance in broader philosophical theories, such as the block universe theory. In this view, time is not a flowing river, but a fixed four-dimensional block of space-time, where past, present, and future all exist simultaneously and are equally real. Our perception of time's flow is merely a subjective experience, like a spotlight moving across a static landscape. If the universe is fundamentally non-local, and if quantum entanglement means that distant parts of this space-time block are intimately connected, then the block universe model finds a peculiar kind of alignment with the non-temporal aspect of quantum correlations. In an entangled system, the connection doesn't exist between a past event and a future event in the usual sense, but rather it's a fundamental property of the entire space-time configuration that contains both events. It suggests that the past and future are not entirely distinct from the present, but are part of a larger, interconnected whole, much like different points on a single continuous line. If the universe operates with such deep temporal connections, even at the quantum level, it naturally leads to profound philosophical questions about free will. If the outcomes of quantum events are, in some sense, already determined by future measurements through non-local correlations, or if all of space-time is a fixed block, does that leave room for genuine choice? This is one of the deepest and most enduring debates at the intersection of physics and philosophy. Most physicists would argue that while quantum outcomes are probabilistic, this doesn't necessarily eliminate free will, as the probabilities themselves are fundamental, not determined by some hidden clockwork. Moreover, our experience of free will arises from the emergent complexity of our brains, far above the quantum level, However, some interpretations of non-locality and the block universe view do push us to re-examine the very nature of choice, suggesting that our decisions might be interwoven into the fabric of space-time in ways we don't fully comprehend. It's vital to stress that these are primarily theoretical interpretations and philosophical extrapolations. Unlike the direct experimental proofs of non-locality in space, probing non-locality in time is far more challenging and currently lacks direct empirical confirmation. Experiments designed to test retrocausality are extremely subtle and often subject to multiple interpretations. The arrow of time that we experience every day, leading from past to future, is strongly supported by thermodynamics, the increase of entropy, and cosmological expansion. Our macroscopic world consistently moves forward, and information only ever travels at or below the speed of light. However, the questions raised by non-locality about the nature of time are not easily dismissed. They represent a frontier of thought, pushing the boundaries of what is conceivable. They force us to consider that perhaps our linear, sequential experience of time is just one facet of a deeper, more unified reality. Just as space is not merely empty void separating independent objects, time might not be a simple progression of isolated moments. Instead, the universe, through its non-local quantum connections, might be a single, timeless, entangled entity, where the past, present, and future are all interwoven into a grand, seamless tapestry. The secrets of non-locality are not just about where things are connected, but fundamentally about when and how those connections persist across the ultimate dimensions of our existence. This fundamental challenge to our perception of time serves as a powerful reminder that the universe's secret connections might be far more profound and far more encompassing than we can currently imagine, potentially stretching into the very definition of causality and our place within the cosmic flow. Chapter 9. Technological Frontiers. Harnessing non-locality. For centuries, the laws of quantum mechanics, with their bewildering superpositions and spooky action at a distance, seemed confined to the theoretical blackboard and the sterile confines of highly specialized laboratories. They were the domain of esoteric discussions among physicists, far removed from the practicalities of everyday life. But as our understanding of entanglement deepened, and as our ability to manipulate individual quantum systems matured, a new era dawned. The very non-local properties that once troubled Einstein are now at the heart of a technological revolution, promising to redefine communication, and even our understanding of measurement itself. We're moving beyond mere observation of non-locality to actively harnessing its power, translating profound scientific discovery into cutting-edge engineering. Perhaps the most immediately impactful application of non-locality lies in the field of quantum cryptography, specifically in quantum key distribution (QKD). In our digital world, security relies on encryption, and encryption relies on keys, long random strings of numbers used to scramble and unscramble messages. The security of these keys is paramount, as a compromised key means compromised communication. Traditional encryption methods rely on mathematical complexity, making it computationally difficult for an eavesdropper to guess the key. But with the advent of powerful computers, including the theoretical quantum computers of the future, these methods could eventually be broken. QKD offers a fundamentally different approach. It leverages the laws of quantum mechanics, particularly the principles of superposition and entanglement, to ensure theoretically unbreakable security. Here's how QKD using entanglement works in principle. Imagine two parties, Alice and Bob, want to share a secret key. They use a source that generates pairs of entangled photons. One photon from each pair goes to Alice, the other to Bob. Because these photons are entangled, if Alice measures a particular property, say polarization of her photon, she instantaneously knows the corresponding property of Bob's photon, even though its state was random before her measurement. The genius of QKD comes from the Heisenberg uncertainty principle and the fragility of quantum states. If an eavesdropper, Eve, tries to intercept or measure any of these entangled photons, she inevitably disturbs their delicate quantum state. This disturbance introduces detectable errors in the correlation between Alice's and Bob's measurements. Alice and Bob can then compare a small portion of their key, looking for these errors. If the error rate is too high, they know Eve was listening, and they discard the key and try again. If the error rate is low, they can be statistically confident that no one intercepted their communication, and they have a perfectly secret, random key that is guaranteed by the laws of physics themselves. This isn't about computational difficulty, it's about physical impossibility. Non-locality, in this context, provides the instantaneous correlation that makes the key distribution efficient, and the quantum mechanics ensures the security. Beyond secure communication, non-locality is absolutely central to the promise of quantum computing. Unlike classical computers that store information as bits, which are either 0 or 1, quantum computers use qubits. A qubit, thanks to the principle of superposition, can be 0, 1, or a combination of both 0 and 1 simultaneously. This ability to exist in multiple states at once is a huge advantage. But the real power of quantum computing comes from entanglement. When multiple qubits become entangled, their states are interdependent, allowing them to represent and process vastly more information than an equivalent number of classical bits. For 9 qubits, a quantum computer can represent 12 combinations simultaneously. This exponential increase in processing power allows quantum computers to tackle certain problems that are intractable for even the most powerful classical supercomputers. For example, quantum computers excel at factoring large numbers, a task that underpins much of modern encryption. They can also efficiently simulate complex molecular structures, which could revolutionize drug discovery and materials science. Imagine being able to precisely model how every atom in a new drug interacts with a specific protein, without having to build costly and time-consuming physical prototypes. Quantum computers, leveraging non-local entanglement, could accelerate this process by orders of magnitude. Furthermore, they hold potential for optimizing complex logistical problems, designing new AI algorithms, and even breaking through fundamental scientific barriers. While large-scale, fault-tolerant quantum computers are still in their early stages of development, the progress is rapid and impressive, with companies and research institutions pouring immense resources into this field. Entanglement isn't just a curiosity here, it's the engine that drives quantum computation. Then there's quantum teleportation. Now, before your mind conjures images of Captain Kirk beaming down to an alien planet, let's clarify. Quantum teleportation does not involve moving matter from one place to another. It's about transferring quantum information from one location to another, without sending the physical particle itself. Here's the simplified idea. Imagine you have a qubit, let's call it Q, whose precise quantum state you want to send from Alice to Bob. Alice and Bob also share an entangled pair of particles, A and B. Alice interacts her unknown qubit Q with her entangled particle A. This interaction causes the entanglement between A and B to effectively transfer the information from Q onto B. After Alice performs a measurement on her system, Q out A, and classically communicates the outcome to Bob, Bob can then perform a specific operation on his particle B, which then perfectly reconstructs the original quantum state of Q. The amazing part is that the original qubit Q is destroyed in Alice's process, and its information is transferred without actually traveling through the space between Alice and Bob. It's the non-local connection of the entangled pair A and B that facilitates this seemingly magical transfer of quantum information. This technology is not for beaming people, but it's crucial for building quantum networks and connecting quantum computers, allowing for distributed quantum computation over vast distances. Beyond these major applications, researchers are exploring other ways to leverage non-locality. Quantum sensors, for example, which utilize entangled particles, can achieve unprecedented levels of precision in measuring everything from magnetic fields to gravity, opening up new avenues for medical imaging, geological surveys, and fundamental physics experiments. The ability of entangled particles to be correlated in ways that exceed classical limits makes them incredibly sensitive probes of the environment. It's important to remember that these technologies are still nascent. Building and maintaining coherent entangled states is incredibly challenging, requiring ultra-cold temperatures, vacuum environments, and highly precise control over individual atoms and photons. Decoherence remains the biggest hurdle, constantly threatening to destroy the delicate quantum connections before they can be harnessed. Despite these engineering challenges, the theoretical groundwork is solid, and the experimental progress is astounding. The spooky action that once seemed to undermine our understanding of reality is now being deliberately engineered, promising a future where non-local connections are not just a scientific curiosity, but a tangible, transformative force in our technological landscape. The universe's secret connections, once revealed through abstract mathematics and subtle experiments, are now being put to work, hinting at a future more interconnected and technologically advanced than we could have imagined even a few decades ago. Our journey into the perplexing world of non-locality began with the familiar, comfortable certainty of everyday experience. We started in a universe seemingly governed by strict local rules, where objects occupied definite places and interactions were confined to their immediate vicinity, propagating only at finite speeds. This was the universe of billiard balls and intricate clockwork, a beautifully simple and predictable machine, elegantly described by Newton and Maxwell. It was a universe where here and there felt absolute, and now was a distinct point in time, utterly separate from then. But this comfortable illusion began to crack with the dawn of quantum mechanics. We delved into a microscopic realm where particles weren't solid, discrete entities but shimmering waves of probability. We met the superposition principle, where a single particle could exist in multiple states simultaneously, like a ghost haunting every corner of a room at once, only resolving its true nature upon observation. We encountered wave-particle duality, a baffling concept where light could be a particle and a particle could be a wave, blurring the clear lines our intuition desperately clung to. These initial forays into the quantum realm were unsettling enough, but they were merely a prelude to the most profound challenge to our local worldview: entanglement. Einstein himself, a titan whose mind forged new understandings of space and time, found entanglement deeply troubling, famously dubbing it spooky action at a distance. It implied that two particles, once linked, remained instantaneously connected, their fates intertwined regardless of the vast distances separating them. A measurement on one, it seemed, instantly dictated the state of the other, without any signal, without any delay, without any known mechanism of communication. This was the fundamental problem of local realism, pitting Einstein's intuition against the strange predictions of quantum theory. The crucial turning point came with John Stuart Bell's genius. Bell didn't try to explain the how of entanglement. Instead, he devised a brilliant mathematical test, Bell's inequality, that would definitively prove whether the correlations between entangled particles could be explained by pre-existing local hidden variables, or if true non-locality was at play. His theorem transformed a philosophical debate into an experimentally verifiable question. Then, through decades of meticulous and increasingly sophisticated experiments, from the early tests by John Clauser to the groundbreaking work of Alain Aspect in the 1980s, and finally culminating in the loophole-free tests by Anton Zeilinger and others in the 2010s, the verdict became undeniable. These experiments, repeated countless times with ever greater precision, consistently violated Bell's inequality. This was not a minor anomaly. It was a profound refutation of local realism. It meant that the universe, at its fundamental level, is either not local or its properties are not real, independent of measurement, and the scientific consensus points overwhelmingly to the reality of non-locality. The spooky action is not an error in quantum mechanics. It is a fundamental truth about our universe. But as we clarified, understanding what non-locality is requires equally understanding what it isn't. It is not faster than light communication, nor does it enable telekinesis, psychic powers, or any form of magic. It does not allow for sending messages to the past. It is a probabilistic, non-controllable correlation that arises from the very fabric of quantum reality, not from manipulated signals. It's a subtle, deeply physical phenomenon, not a metaphysical one. It also doesn't imply that everything is constantly entangled in our macroscopic world. Decoherence ensures that the classical, local reality we perceive emerges from the quantum substratum. The implications of this established truth extend far beyond individual particles. We explored how quantum field theory paints a picture where particles are excitations of omnipresent fields, and how the entanglement we observe is an inherent property of these fields themselves. This suggests that the vacuum of space, far from being empty, is a continuous, interconnected ocean of quantum potential. This led us to the speculative but tantalizing frontier of quantum gravity, where some theories propose that the very fabric of space-time itself might be quantized and entangled, meaning that here and there and even now and then might be far less distinct at the most fundamental level. The EREPR conjecture, linking entanglement to wormholes, represents the ultimate dream of connecting the quantum weirdness to the grandeur of general relativity, suggesting a universe fundamentally woven together. We even ventured into the highly controversial discussions about consciousness and non-locality, examining theories like Penrose and Hameroff's ORC-O, which propose that consciousness might arise from quantum processes within the brain. While intriguing, we stressed the immense scientific skepticism surrounding these ideas due to the challenge of maintaining quantum coherence in a warm, noisy biological environment and the lack of empirical evidence. Similarly, we touched upon how non-locality challenges our perception of time, introducing concepts like retrocausality and finding a peculiar resonance with the block universe theory, where past, present, and future coexist as part of a single unified space-time block. While these temporal implications are far more speculative than spatial non-locality, they demonstrate the profound reach of this quantum revelation. Finally, we explored the incredible technological frontiers opened up by our understanding of non-locality. Quantum cryptography promises truly unbreakable communication, guaranteed by the laws of physics itself. Quantum computing, leveraging superposition and entanglement, is poised to revolutionize fields from medicine to materials science and artificial intelligence, solving problems intractable for even the most powerful classical supercomputers. And quantum teleportation, while not for beaming humans, is a critical technology for building future quantum networks, allowing quantum information to be transferred without physically traversing the intervening space. So we return to our central question: is everything secretly connected? The answer, delivered by the most rigorous and astonishing experiments in the history of science, is a resounding and awe-inspiring yes, not in the simplistic, magical sense of thought controlling matter, nor in a way that allows for instantaneous messages across the cosmos, thereby undermining the very fabric of special relativity. Rather, the connection is far more profound. It is intrinsic to the very nature of reality at its most fundamental level. The universe is not a collection of isolated, independent parts that happen to interact. It is a grand, intricate tapestry, a unified quantum whole, where the threads of entanglement weave together distant particles, and perhaps even the very dimensions of space and time. Our everyday experience of separation, of distinct objects existing independently in a local space, is an emergent property, a macroscopic approximation of a deeper, more unified, and fundamentally non-local reality. The spooky action isn't spooky because it's impossible. It's spooky because it reveals a truth about the universe that transcends our classical intuition. The implications of non-locality are still being unraveled, and many mysteries remain. How does this non-local interconnectedness give rise to the local world we perceive? What does it truly mean for the nature of causality and our experience of free will? These are questions that will continue to drive scientific inquiry and philosophical debate for generations to come. But one thing is certain: the journey into non-locality has fundamentally reshaped our understanding of what it means for things to exist, to interact, and to be connected. It has revealed a universe far more mysterious, far more elegant, and infinitely more interconnected than we ever dared to imagine. It forces us to confront the possibility that at the very heart of existence, we are all, in some profound and undeniable way, part of a single, secretly connected cosmic dance. Connected